Today we'll be talking about SlateDB. SlateDB is an embedded database built on object store. Let me start with my introduction. I'm pretty new to Rust. I started only a couple of months back. I don't use it at my day job. I now do data infrastructure at DoorDash. Before this, I was at Microsoft in Azure Stream Processing. SlateDB is an open source project that I contribute to for fun. It's a passion project. So I'm not a Rust expert. I'm very new. So that's a little bit about me. Now, with that, let's see what the plan for today is. We'll start with the motivation and share why SlateDB was started. I'll share what it is, and then we will get into the internals of how it is built. Let's start with the introduction. Object store is rising. Uh, Things like Azure Blob Storage, S3, and GCP, they offer very attractive properties. You can batch and then increase the latency and at a very attractive cost profile, offer a lot of good performance for customers. We see this in a lot of products. You see something like Warp Stream, which is a Kafka compatible streaming platform. It offers Kafka protocol and it stores all the data on S3. The compute is stateless. All the state is in S3. You see similar thing in table formats like Iceberg, Apache, Hudi, and Delta. They offer table storage over object storage. Now, this was the motivation, and SlateDB is a project that offers key value interface over these object stores. When you look at this, there are three common techniques that are used across all of these designs. One of them is immutable files. Files once written are never changed, and new data creates new files. The second is batched writes. I talked about this for a little bit. Put API calls are some of the API calls that are most expensive. You can increase the batching, and then with that, you reduce the cost. The third is conditional writes. This was not available in S3 until August last year or so. It is available now in S3. With that, it is available in all the major cloud providers. The conditional write, which is write a file if it doesn't exist, along with the technique of use predictable file names such as file number 1, file number 2, and so on. That is used to cause conflicts and so that two different clients don't overwrite each other's data. So these three common techniques are used in a lot of products. That's what is used in SlateDB as well. With that, let's get to what is SlateDB. It's a Rust library. It's an embedded key value store. If you use RocksDB, it offers a very similar interface. There is get and put, and it has range reads. It's implemented as a log structured merge tree. It is useful for cases where a little bit of latency, like 50 milliseconds to 100 milliseconds, is reasonable. Some practical use cases are stream processing, state store, durable execution, durable caches, and so on. There are two companies that are using it in production today. One is Responsive. Responsive is hosted Kafka streams. They use SlateDB for a custom state store, and TensorLake is an AI company. They ingest documents and create context for LLMs. They use it for storing data as well. Now, with that, I'm not sure how much you can see on the screen. This is an example of how you can use it. There is not a lot going on here. It uses the object store crate. You create the object store crate, and then you pass in a couple of properties. With that, you have a database. You see two sections here. The first section is doing a put, and it's doing a wait. What that will do is it will exit only after the data is durably returned to S3. uh, or any other object storage. In the second loop, it's writing 1,000 keys, but you see await durable false. What that will do is the await will exit even before the data is written to object store, and the flush call that is happening at the end, that's what will make it durable. And this is the crate. So with that, I'm going to go into the internals of what happens when you do a put. There are a couple of terminologies. As I shared earlier, this is built as a log structure merge tree. Uh, and the first is the SST file. It is a binary file. It has key value pairs and a little bit of metadata. Two important metadata that is there in the SST files are Bloom filter and what is the first key. There is a little bit more than that. And then there is a terminology called as write ahead log that's used. It uses the same format as SST. I'll share more in the upcoming slides. After that, there is the sorted run. It is a set of SST files, and each of the SST file has non-overlapping keys. Manifest file shares the state of the database at any point in time. So the state of the database is the set of SST files that are part of the database. With those terminologies, let me get to the writes. In the next slide, I have a sequence of what happens, but let's start with this picture first. There are two sections that you see here. One is the memory section. The second is the object store section. When you do a put, all the data is in the in-memory structure called as wall in this picture. And at some frequency that's defined by the user, that's returned to object store in the folder called WAL. Here we see 73.sst. That's the first write that happens to object storage. And there is another property called as L0 SST size bytes. When that limit is hit, it also creates a file in the compacted folder. Writes are durable the moment the data is written to wall, and these files are numbered, so two different clients will not overwrite each other's data. This one shows what happens in each of the step. In the first step, what we see here is it's doing a wait, and when it does that in the object store, it would create it would create the 001.sst. In the second statement, it is not waiting. In that case, nothing changes in the object store. And when you flush, you see that there is another SST that's getting created. Finally, in the fourth step, let's assume that a lot of keys were written and we hit the L0 SST size bytes. There is the XYZ SST that's created, and there is a new manifest. In the manifest, you see that L0 has the file xyz.sst. There is one more property here that is interesting. That's the last compacted. There you see the number 2. What that means is write ahead log 0, 01, 002. They are no longer part of the database. They are in the xyz.sst file. So that's what happens in write. As I'm describing this, I'm skipping over some of the details to fit it into the 30-minute or so of talk. It also creates empty wall on initialization and few other aspects that I'm skipping today. The next thing that is interesting here is compaction. Compaction is taking a set of files, creating another set of files that is more optimized. I'm not getting into the details. if someone is interested, I can get back to this later. Now let's assume that a couple of writes have happened and a couple of compactions have also happened. This is an example of how the state would be in object store. What we see here is there are multiple write ahead log SSTs. There is one called like 73.sst, and you see compacted has additional folder files, and there are a lot of manifests. All these files are immutable. Okay, now let's look at the manifest and okay, let's look at the manifest and look at some of the properties. The first one is straightforward. It is a manifest ID. Every manifest has an ID, and it increases from 1 to 3 and so on. Writer epoch is the epoch of the writer that created this manifest. It's also incremented every time a new writer is created. There are few other properties. Here I'm showing a simplified manifest. I talked about the wall ID last compacted before. The other one, L0 last compacted. Every time compaction runs, that particular property is updated. Two other properties, L0, that is the set of SST files that's waiting to be compacted, and compacted is a sequence of sorted runs, and each sorted run is a sequence of SST files. That is what is there in the manifest. Every time an update to the database happens, a new manifest is created. There are a couple of different kinds of updates that happens. When a new writer is created, the epoch will be incremented and a new manifest will be written. When an L0 file is added, then the array that you see here that talks about a list of L0 SSTs, that particular array will be updated and a new manifest will be written. Compaction, when it creates a new sorted run, that would also update the manifest, and writer initialization will create the manifest as well with the incremented writer epoch. So essentially, every time a change to the database happens, a new manifest is created. Reads are very similar to the writes. It starts with the mem table and goes down the stack in the sorter runs. And again, L0 has overlapping keys, and the sorted runs have non-overlapping keys. Okay. So I talked about L0 creating an SST file and then updating a manifest. And I also talked about write ahead logs that are no longer part of the database, but are there in S3. So these operations create files that are not referenced by anything anymore. Also, every update creates a new manifest. So there are a lot of these files lying around. Garbage collection process kicks in at some frequency, and then it deletes those files. Compaction is another kind of a maintenance operation. Compaction, it is a regular LSM compaction. And the interesting thing about the design of not having any state and keeping all the state in S3 is that these maintenance operation can now run in a different process, in a different machine. And this is how one of the users or responsive, I think, they do run it in a separate process. Now let's talk about checkpoints and snapshot reads or time travel reads. Because every change creates a separate manifest, you can use an old manifest and open a read-only database that will give you the state of the database as of some time back. That property is very interesting for something like a state store, where you could have two different consumers, and each consumer is looking at the database at a different point in time. And in Delta, this is kind of marketed as time travel reads that comes for free with this kind of design. Now, I talked about garbage collection, and I also talked about reading from an old state. So garbage collection can delete the files that are not referenced by the current manifest. So to avoid that from happening, you can checkpoint. All that is going to do is there is a checkpoints array, and that will be updated with the ID of the manifest that you want to be checkpointed. The other interesting thing is the writable clone. Because all of these files are on S3, it's very, very easy to create and very cheap to create a writable clone. The only thing that had to change in the manifest is a reference to a parent database. So the metadata is copied over, but the actual SSD files are still referenced. With that, you can easily create a writable clone and continue. And these two databases can continue to exist independently. So with all of that, here are the features: zero disk, a single writer. You can have multiple readers. There is caching implemented as well. Uh, things like manifest files, the metadata, Bloom filters, even the SSD files, all of that can be cached locally, improving the read performance. There is snapshot isolation and compaction that can run independently. There is checkpoint and writable clones. And here are three things that are coming up in the future. One is language bindings for other languages like Java. Transactions, the RFC is still being discussed. That will be coming up soon. Change data capture is coming up soon as well. That will let you continuously stream the state of the database to another system. And that's what I had. So this is the crate, and there are a couple of good first issues, including documentation updates and few low-hanging fruits if you're interested. Yeah, that's it. Questions?
Mic check.
Hello. Question. You mentioned garbage collection and sorting. So is it some separate process that's running, or it's writer? How it's happening? Like it's library, right? So for garbage collection, you need somehow invoke this garbage collection. You need somehow invoke this compaction. So how it's happening?
Yeah, there are two ways in which it can happen. There is a admin utility. You can run that admin utility, and then it can do a one-time compaction. Or the process that is the writer can act as the garbage collection as well. It has a thread that wakes up at some point in time and does it. Or you can have a separate garbage collection that will continues to run and again only kick off garbage collection at some point. So you need something that's long running.
Okay. Second question is about single writer. So what exactly it mean practically? It's like only one thread can write?
Yeah, what it means is you can have multiple threads that can write, but there is only a single process. At the initialization, what happens is a new manifest gets created and an empty write ahead log is created. So let's say you had a second writer that will attempt to write a write ahead log, and it will hit a conflict and it will exit. The principle that we want to keep is that there is only one writer that is active.
Okay, thank you.
Hi. So I've only used S3 a little bit, but my understanding, and correct me if I'm wrong, is that in theory, I could take my little keys and values and just throw them directly in S3 and treat it as a key value store.
Yep.
I assume that would be really slow and expensive or both and other problems. So is that because S3 should be doing a lot of this stuff and they just haven't done it yet? Or how do I understand like why S3 isn't good at doing this kind of thing?
So S3 is designed as an object store for storing a little bit larger files. Uh, it is not even intending to do something like a key value store. There are other services in AWS that does it. And yes, you are right. If we could just keep it in S3, but then that will be expensive. You need to do some kind of a batching, and then you need a way to organize these files. And that's what SlateDB does.
I'm very inexperienced with any of this like cloud infrastructure stuff. So this is probably a super basic question. How do you think about like the natural limits of this approach? Like what does this, where does this hit the wall? Where does this stop performing? Where like what would limit this from being used on any kind of like key value problem?
Yeah. There is a benchmark that is on GitHub. This thing that runs every day. You can look at the numbers. There will be two kinds of limits. One is S3 will have limits on throughput and the number of operations that it supports on a particular bucket. So that's the first kind of limit. And the machine that it runs on, that will have some kind of a limit in terms of amount of operations per second that it can do. So that will be the second kind of limit. There would also be a back pressure. I was talking about these L0 files and all of these compactions that are happening. It is possible that the writes are happening so fast that the compactions are not uh, happening, because and with that the read performance will be very bad. So there are some defaults that are set in terms of if it is falling behind a certain number of compactions, then stall the writes, right? So those three kinds of limits would be hit on specific numbers. I don't have it right now, but it is available through the performance runs.
Sorry, I have low voice today. So just before asking my question, I want to understand, you said that you will batch writes, right, to optimize performance. So what happens if while you're writing on the wall, things are batched, the process die? Do you have data loss? How do you have some sort of journaling? How do you figure out if things, as you were writing, were batched, what went through, what didn't go through, and if you can recover the data that you were writing?
Yep, that's a great question. Yes, there will be data loss, and I shared a couple of use cases where this is applicable. It is durable only after you call flush, right? Sometimes when you call flush, there is nothing to write. The flush milliseconds frequency kicked in, and then it wrote the data. To be sure, it's always important to call flush. But the use cases that I was talking about, let's say state store for stream processing, your data is already in something like Kafka, and you are reading that and then doing some transformation. And as you do that, you persist in the state store, and then you send it to your output, right? Now, you can control a lot of this in a process like Kafka streams. There, it's okay for you to not flush on every write.
Do you have a way to know what was in the queue to be flashed? Let's assume you have a Kafka stream. How do I know what um, what items in the stream went through the pipe? Do you have some sort of journaling in process? Or is there any plan to have some sort of journaling?
That journaling will be in the user application. So yeah, in the case of Kafka streams, that the Kafka streams program will have that kind of journaling. Thank you.